Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss vector atom model of atom, or we can say it as coupling of orbital and spin angular momentum. Let's begin. Same concept. When an electron is revolving around that of nucleus, it executes a orbital angular momentum, and again due to the spin of that of electron, means the electron rotates its own axis. A new type of angular momentum known as the spin angular momentum is generated. So one is orbital angular momentum and another one is spin angular momentum. These two are vector quantities. So the resultant of these two creates a new momentum that is known as total angular momentum. So the total angular momentum results due to two types of angular momentum. One is, that is the combination of orbital angular momentum plus the spin angular momentum. Spin angular momentum. Total angular momentum is the sum of orbital angular momentum and spin angular momentum of that of electron. Since the angular momentum is a vector quantity, we can represent the total angular momentum by means of a vector. That vector is obtained by the vector addition of orbital angular momentum and spin angular momentum, that leads to the vector model of atom. The sum of these two vector, or the resultant of these two vector, results the total angular momentum, and that model of an atom is known as vector model of atom. That is the vector model of atom. Let us do. Consider an atom whose total angular momentum is provided by single electron. We consider a single electron atom like hydrogen, lithium, sodium, etc. Since the total angular momentum of closed cell being 0, that's why we prefer this type of atoms, and the magnitude of orbital angular momentum of an atomic electron is given by total angular momentum is the sum of orbital angular momentum and spin angular momentum. Let us define first orbital angular momentum, then spin angular momentum, finally its resultant. First of all, the magnitude of orbital angular momentum. The magnitude of orbital angular momentum that is magnitude of L, that is L, that is L whole into L plus 1 under root H cross, where L is the orbital quantum number and its z component, z component means Lz is equal to ml h cross ml h cross, where ml is known as magnetic quantum number. Here we write where small l as orbital quantum number, and ml is the magnetic quantum number, and the allowed values of ml will be 12 plus 1 allowed values, and that ml stands for plus L to minus L region. Okay. Similarly, this is for orbital angular momentum. Then for spin angular momentum, similarly, the magnitude of spin angular momentum, that is the magnitude of s vector equal to s, that is the small s plus 1 under root s cross, and its z component, that is sz is equal to ms h cross, where small s is the spin quantum number, that is the spin quantum number, and ms is the spin magnetic quantum number, that is the magnetic spin quantum number, and again it has the allowed values of 2s plus 1, and the spin is plus minus half. The ms value will be plus half and minus half. This is for orbital angular momentum, and that is for spin angular momentum. Then the total angular momentum, that is the sum of orbital and spin. Therefore the total angular momentum of one electron atom referred as J vector, capital J vector, is the vector sum of L vector and S vector, that is J vector is equal to the vector sum of L vector plus S vector. Similarly, according to the condition of quantization for total angular momentum, that must be associated with total inner quantum number j, like that of, since the angular momentum is associated with that of orbital quantum number, again the total angular momentum is associated with that of total inner quantum number. So we can write here magnitude of j, that is the j is the small j plus 1 under root h cross, and its z component, that is j z is equal to m j h cross, where j is known as inner quantum number, small j, that is the inner quantum number, and mj is the total magnetic quantum number, that is the total magnetic quantum number. Since look here, the z component of L, that is ml h cross, the z component of S, ms h cross, and the z component of j vector, what, mj h cross, these three are scalar quantities. So since these three are scalar quantities, we can write, since z component of L vector, j vector, and s vector, the z component of orbital angular momentum, spin angular momentum, and total angular momentum are scalar quantities, So the z component of total angular momentum is equal to the sum of Lz plus minus Sz, and mj and the total magnetic quantum number, again that is the sum of orbital quantum number plus minus spin quantum number. Since ml is an integer and ms is the value like plus minus half, so mj must be a half integral, as we write here. What is the value of mj here? Since ml an integer and ms, that is plus minus half, so mj will be half integral, is half integral. So the maximum value of mj, ml and ms are what? The maximum value of mj stands for j, maximum value of ml stands for the maximum value of the maximum value. The maximum value of mj stands for j, again the maximum value of ml stands for l, and the maximum value of ms stands for s. Is the maximum value. The values within that of range plus j and minus j, within that of range plus l and minus l, within that of range plus s and minus s. Okay. So what we can write here? So since small j is the sum of small s plus minus small s, since j vector, l vector and s vector are all vector quantities, so they must have some specific relative orientations. The orientations look like this. What are the orientations? Since these three are the vector terms, the orientations will be what? We in all the conditions we consider one electron atom. The consideration is one electron atom. What should be the orientations in between L, J and S? So J is equal to L plus S. So here J, capital J is greater than L, and another orientation J L minus S, so J is less than L. So L and S, L vector and S vector added vectorically are added by using vector addition rule to produce what? To produce J vector, in two ways. Two ways are given as L plus A and L minus S. So how these two are formed? Taking as here is the L vector, that is L vector, that is S vector. So the resultant will be, that is the direction of L, that is the direction of S, so the resultant will be the opposite to that of direction, that is the J vector. And for that of case small j, the sum of L plus S, we consider what? We consider one electron system. So putting the values as S is equal to 1, sorry, L is equal to 1 and S is equal to half, that will be 3 by 2. Again for second orientation J is equal to L minus S, it will be, let we prefer as, that is for L vector, this one is for S vector. So that values will be J vector. Again small j is equal to L minus S, L is equal to 1 minus S is equal to half, the value will be half. That is the two orientations as far as the vector atom model is concerned. Look here, the angular momentum of atomic electron L and S, just I write here, the angular momentum of atomic electron, angular momentum L and the spin angular momentum, that is S, are interact, these two are interact. In which way? They interact in magnetically, they interact magnetically, which is known as spin or spin orbit interaction, that is known as spin orbit interaction, spin orbit interaction. Other atom behaves like an magnetic dipole. Since the interaction is known as spin orbit interaction, they exert torque on each other, they exert torque on each other. These internal torque do not change, these internal torque don't change. Since the magnitude of vector L and S don't change, that internal torque don't change, change what? The magnitude of L vector and S vector. That internal torque can't change the magnitude of L and S vector, but that not change the magnitude, but it cause what? It precedes uniformly around their resultant J, but cause them to precede means ghurnana, to precede uniformly, around their resultant J, around their resultant J vector. Okay, that means if the atom is in free space, then the external torque act on it and the total angular momentum J both are conserved with each other, both the magnitude as well as in directions. So the angle between L and S remains invariant. So how is it, how the precision takes place? Look here, how the precision takes place. Just I took a figure here. That is S, that is L vector. So the resultant will be J vector, resultant will be J vector. That precedes, this is the spin, precision of spin. then the precision of L will be what? The precision of L. Okay, how the precision takes place here. Again, when another condition, when the external torque, if the atom is free in space, then what happened? When if the atom is in free space, then the external torque act on it, and total angular momentum J vector is conserved both in magnitude and direction. So the angle between L and S, the angle between L vector and S vector, that is the angle between L vector and S vector, that is the angle is the theta, that remains constant always, So here we use from cosine law, J square is equal to L square plus A square 2 Ls cos theta, which implies cos theta is equal to J square minus L square minus A square divided by 2 Ls. Again, cos theta can be written as, this is the angle between L dot S, at the cosine of angle of L and S. So in place of J square we can substitute J equal to J plus 1 H cross. So in all terms H cross and H cross in the numerator and denominator cancel with each other. So we have J whole into J plus 1 minus L whole into L plus 1 minus S whole into S plus 1 divided by 2 whole into, that is L whole into L plus 1 and S whole into S plus 1 square root. It is the vector model of one electron atom. It is the vector model of one electron atom. And it can be extended to many electron atoms, and this is very helpful to explain the fine structure of spectral lines and anomalous Zeeman effect with the hyper fine structure. So with the help of this video lecture we understand what is the coupling of orbital and spin angular momentum, that is the vector atom model of atom. We take first the orbital angular momentum, then spin angular momentum, then add it vectorically to find the total angular momentum. Then since the resultant is a vector, there will be two types of orientations. According to the two orientations, two figures are done. So what happened technically inside that of vector atom model, there will be a spin orbit interactions. According to that of spin orbit interaction, a torque executed, but that torque does not change the magnitude of L and S, but cause to precise it around that of resultant J vector due to that precision. But in case of free space, what happened? This is conserved, and again this is nothing, that one is the vector atom model of one electron atom, and it is very helpful to define or to explain the fine structure of spectral lines, anomalous Zeeman effect, and hyperfine structure. So with this useful and informative notes, let me wind up this session. Thank you.